Okay, good morning. So I'm going to talk a little bit again, about our general theme here of limits and opportunities in online education. I have to say up front, I'm not really doing online education, so I may be marginally qualified here. I am kind of an observer in that at Arizona State University, we are putting our full bachelor's degree in electrical engineering is now being put online. And there's some people who are working very, very hard to do that, and so I'm kind of following that as an interested observer. What I am doing is I'm kind of working on some step-based tutoring software I'd like to tell you about, which I think would be actually very useful, and in fact it is already being used the first time this semester in our online class, as well as all our on-campus classes as well. And so I'd like to tell you about this kind of tackling the homework and interactivity end of things a little bit. So just briefly, I want to acknowledge all my collaborators, all my very hardworking students who have helped to develop all this software. I couldn't possibly code it all myself. And then a number of other faculty at other institutions are helping to test us now as part of this NSF-sponsored project. So first of all, just to talk a little bit about some of the limitations and opportunities. Obviously, and a lot of this we've already heard about in the previous talk, so I'll go through this rather quickly. I think they've given you a very good overview. But one of the things I worry about is delivering the upper division laboratory courses. Things that involve building electronic widgets. You can have them do that with a kit or whatnot, but being a solid state guy, I think about how we're going to teach our clean room processing class online. That's a little bit more challenging. We're not going to ship the diffusion furnace to the students and things like that. So that's, I think, a real big challenge. Perhaps some of these simulated laboratories, again, but we already heard some very interesting discussions, so I won't dwell on that. I think that students communicating with each other is obviously more of a challenge when you're going online. You have to develop good facilities for them to do that, especially if they're trying to do team projects. And related to that, I think informal interactions both between students and with students and the instructor. That's becoming a little bit more difficult. They can't just come up after class and start casually talking to questions. So you have to make sure that there are mechanisms to try to partially replace that. Of course, the student body is different in online, as we just heard, for example. And they may have more travel obligations, family obligations, and since many of them are, of course, working full-time, or most of them probably, then they have more other time commitments than other students, and that requires a little bit different approach. And then, of course, developing those materials. Boy, that is a major challenge. I know one faculty member of our department spent developing an introductory electromagnetics course. I think reports he spent 900 hours developing that course for the first time. Imagine, that's just a fantastic amount of work. And he ends up with a very high quality product, but the first time development is a major activity. And then, of course, online assessments pose their own challenges. As you mentioned, somebody mentioned fraternity files and things like that. So there are obviously some big issues there in terms of how do you enforce academic integrity. If you're using online assessments, you have to have some sort of proctoring system or something to deal with that. And of course, the students, maybe a very different student body than you have on campus, tends to be a little bit more homogeneous. Online students may have very wide variations in their background, their skills. Do they still remember how to do an integral, or do they, that kind of thing? Are they up to date on their academic skills, their ability to study? And that, of course, depends a lot on your admissions policies, too. So you tend to get a really wide variety of people applying to these online programs. A lot of people have maybe tried traditional programs and didn't quite succeed the first time around. Now they're going to do it online. And, that may work if they're more motivated, more mature, but still it can be a big challenge. And, of course, then we also talked about the grading being automated. Again, that's obviously poses some limitations, and that's one of the things we're trying to deal with here. But then, of course, on the flip side, there are many opportunities. These interactive materials, once they're developed, can be hopefully much more effective than the traditional lecture type of things that many people use. I think there's a lot of opportunities for educational research. This, to me, is one of the most exciting things about online education that you can do, is using tutorial software, you can collect tremendous amounts of data. We have hundreds of thousands of log entries now in our system from students using the material, and you can learn an awful lot by going and mining that data and trying to understand where students are having difficulty. And I think that allows you to do a lot of experiments that you couldn't easily do in a regular classroom. You can't lecture 5 different ways, but you can program your system to give students 5 different approaches and then see which one works better if you're doing an online type system. And you can also, obviously, accessibility has already been mentioned. A wider variety of students can gain access to advance their careers. Students may be more motivated and more mature than the traditional 19 or 20-year-olds. They have real-world experiences, which obviously can be a tremendous asset to bring into the classroom. And of course, once you've got these things developed, then it may be somewhat less effort to deliver them, although I think that's debatable depending on how it's done. And of course, this highly interactive software can give you student feedback that can lessen the need for traditional grading to a degree. And of course, we can try to tailor this to individual students, to their needs. So our question we're trying to address is how can you use this interactive step-based tutorial software to assist in this online learning as well as the traditional classroom-based learning. So just to talk about the software then, these online courses as well as MOOCs and conventional instruction, we all need interactive, engaging tools to help supplement traditional instruction. But of course, the direct interaction is more difficult. So, and then one of the topic areas we're talking about here is linear circuit analysis, which of course is more interesting to the electrical engineers, but it's also very widely taught in foundational class taken by many majors. And so we have thousands of students every year taking this course. Traditional homework, we get limited and delayed feedback. If they're doing it on paper and turning it in, then they may not find out till a week later what happened, and by then they've gone on to new topics, and it's really not very effective at all. And so hand grading, of course, is required for that kind of thing, and that can be very difficult in online courses without some very innovative technology. So then you say, well, but the textbook publishers all have these things available, right? They have these big websites with what are mostly answer-based tutors. And so basically somebody works through a circuit problem or some other type of problem, and they work through maybe pages of work on paper, and then they put in their final answer in the computer. And the computer says, well, sorry, didn't get it, but try again. And the student says, well, that's great, but where did I go wrong? And the computer says, somewhere. So it's not very helpful. And it takes students, I've had students come into my office and say, oh, I just spent 12 hours trying to solve that problem. Wow, that was a lot of wasted time there that could have been spent more productively learning. So that's what we're trying to do, is to capture all those individual steps that people take in solving a problem and be able to give them immediate feedback. So the step-based tutors, which we're developing, are known to have effect sizes of around 0.76 standard deviations compared to expert human tutors, so very comparable to that. And much better than the answer-based tutors, which are about 0.31. This is based on a meta-analysis. Of course, this can vary a lot from course to course and program to program. And our software, just to give you a preview, we're getting up to about 1.21 standard deviation. So it seems to be working fairly well. We can provide fully automated feedback, which again is great for the online environment. So what we're doing in particular is, and I'd rather just demonstrate this rather than talking about it so much. So I just installed our software here. So here's an example of a circuit, and what I do is I just push a button here, and just in demonstration mode. So there's a brand new problem. Okay, that problem was not stored in memory or disk or anything like that. That was just created by the computer in an instant. So every student is getting a different problem. Every time I push this button, I'm getting the same kind of difficulty, the same type of complexity, but it's brand new. That problem has never existed before. So there are no exam files. There's no way of, and if somebody wants to help somebody else, well, they have to do twice as much work, which tends to damp that down a little bit. Quite a bit, actually. Tell people if they want to help their friends, they got to be really good friends now. So, and also we have the solution. It's completely automated generated. This is more of an example. So here we've written the nodal analysis equations, for example, for a circuit. That's all been generated. And then there are detailed explanations available for these things as they go through. They enter these things on their own. I don't have time to demonstrate all the interactivity, but basically they'll get immediate feedback. If they enter something wrong, they're told that it's wrong, and then they get explanations too. And if they give up, well, they just push a button that says, I give up. Student said, the computer says, that's fine. Here's the fully worked answer, solution to your problem. And with a detailed explanation of every step in that solution, okay, now you've read that, here's another problem, just like it. Okay, we never run out of problems. So some students go through these things in 8 or 10 minutes if they already understand it. Other people take 2 hours to go through the same material. So it really allows for students to get what they need basically to achieve the mastery, but they're required to basically achieve mastery learning on each topic before they go forward. And so that way we ensure that the students are really learning the material as opposed to they've tried to work X number of problems and failed. That's not what we consider mastery. So they really have to go forward and genuinely learn the material. So as I said, we have, oh dear, what did I do? Pushed the wrong button there. So we generate completely new problems, and basically we have an unlimited supply of examples. The textbook now, instead of being this thick, it can be maybe this thick, and it'll contain all the same material, because most of it, after all, is this stuff that we're generating. And of course, the textbooks are full of mistakes. this is free of mistakes because it's, at least once you've got the algorithm working, and that's a big, big advantage. We accept many forms of student input. We allow them to redraw circuit diagrams on the screen. They can enter equations using a special template-based interface that provides some scaffolding to teach them what the equations basically should look like. They can put in, they can sketch waveforms interactively, graphically on the screen to draw what a waveform would look as a function of time. Put in simplified algebraic or matrix equations. They can put in numerical answers, multiple choice. So all of these things are accepted into our system and immediately evaluated. So every step in the process, you say, if you redrew that circuit diagram improperly at the beginning, we're going to stop you right there, because going on writing the equations for that, that's a waste of your time, right? You're not going to get the right answer. So we have to really stop and identify the place where they went wrong and tell them right away, and then give them feedback. And again, give them the solution if necessary. Just say, this is how you do it. It's like giving an example, but it's in real time, and they've already been studying it, so it makes more of an impact. We explain the wrong answers and the correct solutions. And another thing we're trying to do is to address common qualitative misconceptions that are often ignored in conventional instruction. So we have a lot of focus here on specific qualitative ideas, and we have qualitative problems that we're putting in. And special pedagogical features such as coloring nodes or equation terms in a special way that helps the students understand the circuit better, and which is, for some reason, never done in textbooks. They only use the colors to make it look pretty. They don't use it really for functional purposes. So here's just an example. I won't really bother to explain how we generate. This is actually the hard part, is making the problems. Solving them is relatively easy. But we use a special three-step algorithm because this is actually very challenging to generate a problem automatically. So we're well over 100,000 lines of code and counting to do this. But it works very well when you get it done finally. And there's an example of a fully worked solution. So we have the equations, we put them in simplified form, put them in a matrix equation, then we actually solve it numerically. And basically that's just an illustration. And there's another example. This is from AC analysis. So they're doing a mesh analysis here using phasors, and so they put everything into complex impedances, and again, it writes all the equations, and they can do that. And here's just an illustration of how you can interactively edit a circuit on the screen so they can change values. Say if they're doing a superposition, they can turn off some of the sources by changing them into shorts or opens as appropriate. Or they could redraw a source transformation on the screen. And so they have this very interactive editor, sort of like a PSpice type of editor, but it's much more constrained than that so that they don't have as many places to go wrong, basically. But they have a full-featured editor they can use. And here's an example of the equation entry system. Here they have a palette of the different types of terms. So depending on the type of equation they've selected, it gives them the different types of terms that they might need. And then they're responsible to select these and drag them down into this area, basically, however many terms of the different types. Then they go through and they just quickly fill in the blanks in these equations. And then they check the button. Basically, it says check the equation, and it right away goes, ta-da, if you got it right. Or if not, then it basically says, you didn't do it correctly. And again, if you get in trouble, you just give up, and it'll give you the full solution, explain all the details to you, and then you go on and try another problem. So again, example of the interactivity. Over here, we have them sketching a waveform. So we've given them, I think in this case, it's the current through an inductor, and they're being asked to sketch the voltage across that inductor as a function of time. So basically integration, differentiation type exercise. And here they can either do it graphically, they can put numbers in here, and then it automatically generates the equations and so forth. Or we could have them put in the equations. And in any case, it checks all their work as they're actually doing it. And then here's something that's more qualitative in nature, where they're just learning about one of the most important principles, which is circuit elements that are in series and parallel. So they can just go on the circuit diagram and they check the things that they think are in series and parallel, and they click the button. And then in this case, it's telling them, well, you've picked something that's not correct, and it tells you why. Or if it is, then it gives you the congratulations and goes on until you basically learn to do that. And they actually find that this really helps a lot in solving subsequent problems. It's something that most books spend half a page on, and yet that's half the problem students have throughout the course, is learning this concept, and it tends to get ignored or glossed over in the textbooks. And then finally, just the question is, does this work? These are preliminary results. Basically, we did a laboratory-based study, controlled, randomized, brought students into a laboratory, paid them $50 each to come do it. And then we had half of them, they all take a pre-test and a post-test to measure their learning. And then in between times, we either had them work problems out of the textbook, just like they normally do in most classes, or they used our software for the same period of time. And basically, the pretest scores were abysmal. They were about 59%. And these are students actually had already completed the course, or were already in the course. They'd covered this material, so they should already know it, but of course they didn't. And if they worked textbook problems for an hour, basically they went up by 3 points. Okay, 3 points out of 100. If they used our software for an hour, they went up an average of 29 points. So we felt that was fairly effective, about 10 times higher learning increase. The Cohen d-value, 1.21 standard deviations, statistically significant. And also, when we asked them, how they like the materials in terms of different aspects, again, there's about a 1 sigma improvement there in several of these important scales in terms of how it affects their motivation and so forth. And also, there's just some typical comments, and I like the ones that says, I haven't even learned it yet in lecture, but yet it was really easy to grasp, and so he's really excited that he's able to learn these things interactively. So, yes?
Have you tested students a year later?
No, and that's definitely a very important thing, and I think the retention is really the biggest issue here. But right now we're just trying to build the system and get it, do the initial testing, but you're absolutely right. The retention is a very, very critical thing. Yes? Yes. I think we'll just basically, so just run through the conclusion. Just a software tutorial system, about 10 times as much learning. Students find these games to be very fun and engaging. We do, while I didn't say it, we log all the activity to a central server, and we can analyze that data later on. And we think it can be extended to a number of introductory level courses. Obviously, it's not suitable for every type of course, but for things where they're doing introductory analysis level type problems, I think this could actually be extended to a number of different engineering subjects.